So we've finally finished cleaning our data, and we get to the fun part, which is seeing what it looks like. So let's do that now. So we'll start with just a couple of convenient variable names. So we'll just call our clean dates the months to make it a bit easier to see what we're referring to. And the C levels mean C levels, we'll call those levels. Okay, and then we can just plot. So we'll start by doing a scatter plot of the levels against the months. So on the x-axis we've got the months, on the y-axis we've got the levels, and then we'll show the plot. Okay, so that's all of our data, all of our cleaned data against over time. So we can already see there that we can see that we're getting a bit of an upward trend there. We'll look at that a bit more closely. First though, we might do a line plot, because it's difficult to see from this exactly what's happening from month to month, because the dots are so close together. We don't know if it's wiggling around here then coming down here, or whether it's going like this. To do a line plot, we can just use plot, as we've seen before. Okay, so this one actually shows the similar trend to what we think we're seeing here, generally upward trend, but it shows a bit better what's going on there, which is quite interesting actually, because it's got these oscillations that occur. If those were daily figures, we might think those are the actual tides, but we see these oscillations from month to month. They could still be related to tides, depending on how the cycle of the tides interlaces with the cycle of the months. But anyway, we can also see there, it's easier to identify some of the missing data. So this line's come across here because there's some values missing in here, for instance. So the data appear to have this increasing trend, but we're just going on, our eyesight, and we want to start to look at how we can quantify trends, and that'll be an important part of the rest of the course, is how we quantify trends. So one way we can do that is by comparing what we see in the data with other functions that we know more about, and see how it compares with those. So we're going to start with one of the simplest functions that we know something about, and that's the mean. See how it compares with that. So to do that, we will just introduce some more handy NumPy methods, and the first one is this linspace method. So NumPy's linspace method is similar to Python's range method or NumPy's arange method, but whereas range and arange we put in the starting point, the end point, and the step size, and the end point may or may not be within the values depending whether the step size steps right over it or not. In linspace we put in the start point, we put in the end point, and we put the number of intermediate points we want to have in between. So that means it always finishes on that end point, and effectively it's adjusting the step size instead. Okay, so we've got start, stop point, and the number of samples, and the default value there is 50. So let's have a look at that. So let's first compare it with range and arange. So if we do something like list range, and let's say we go from 0 to 9 with a step size or stride of 2. Okay, we end up with 0, 2, 4, 6, 8, and then 10 is past that end point. If we do instead a numpy arange, we'll see a similar thing. Okay, so from 0 up to 8 again, and finally if we do linspace, and we go from, so this time we're going to go from 0 to 9. Remember, we specify the number of sample points for linspace. So the equivalent of, so we've got 5 samples here, so we're going to put 5, and you can see the difference. So again, it's generated the sequence of numbers equally spaced, but stops at 9 and adjusts the middle ones accordingly. So I mention that because this is a really useful function, particularly if you want to plot, for example, functions. You want to plot a sine function or a cos function or an exponential function or a linear function or a quadratic function. And we will be looking at some of these functions as ways of comparing the data we see with trends that we know about. But we'll start off with an example just using standard trigonometric functions, sine and cos. So let's say we want to plot the sine function. Well, we can start off by setting up our x values. So let's say we want to go from, we want to plot it from minus pi through to pi. So we can do that from minus numpy.pi, so constant defined within numpy, to positive numpy.pi, and we'll just use the default for now, which is 50 values. Okay, so it's divided up from minus 3.1415 etc. through to positive pi into 50 equal values, and we can then use that to plot. So in this case we're going to plot sine and cosine. So x's here are going to be our x values, and that's going to be a linspace from minus pi to pi. We're going to generate our y values for the sine curve, which is sine of the x's. The y values for the cosine curve is cos of the x's, and then we're just going to plot those using plot. And there they are, so relatively easy. Now, it's just worth knowing that although this looks like smooth functions, we haven't asked it to do anything here that's a smooth function. All we've done is we've worked out the y values for 50 different x values, and we've plotted it, and plot joins up the dots, so it looks like a smooth function. If we have enough dots, it looks like a smooth function. If we have fewer dots, it'll look less smooth, and hence sometimes we want to adjust that number of values from 50. We can see that if we do it as a scatter plot. Okay, so now we've plotted the actual values that are really plotted here, so they're being filled in for us there, but these are the real values that we're plotting. when we're dealing with trigonometry, we're dealing in multiples of pi for something like this. On our x-axis, we've just got the numbers, so pi is 3.1415, etc. Is here somewhere. So that axis is not really very helpful for us. We'd rather have this to be in multiples of pi. There's an easy way of doing that. I mean, we could do this by manually putting in our tick labels and adjusting that. An easier way is just to do this a little bit differently, where our x's now are going to be in multiples of pi instead of in multiples of 1. So they're going to go from -1, which is going to be minus pi, to +1. And then our signs is sine of x's times pi. So we've multiplied the pi in at this point. We've plotted them, and in this case we're just going to label them as well. So we'll label, so we know which one is the sine, which one is the cosine, and just to remind us that we're in units of pi down the bottom rather than in units of 1, we're going to put a pi on the x label, and just so happens that that's the escape code for pi. So let's give that a go. And there it is. So we've got pi on the bottom here. This goes from pi to minus pi, and of course that's our cos function, that's our sine function. So how's this relevant to our mean sea levels? What we want to do is we want to plot the mean against our sea levels, but the mean is just one number and we want to plot a line. So remember that when we're plotting in pi plot, we're actually plotting points, and we can join those points up with a line if we think it's useful to do so, but we need the points. So rather than one mean point, we need a number of mean points to draw that line. Okay, so NumPy provides us with a mean function, and another handy one is ones like. We've already seen zeros like. We've used that quite a few times. Ones like's the same, except it just uses, so it sets up something that's the same size and it fills it with ones. So what we want is this, what is essentially a constant function, y equals the mean of x, and we can do that by setting up an array of ones that's the same length as the x-axis, and then we multiply those ones by the mean to bring them up to the right level of the mean. Okay, so here's an example. Mean's 42. If we get ones, we get 5 ones, and then we can say our mean line is the mean times the ones. So it's important to understand exactly what's happening here. So ones here is an array, which is a one-dimensional array with a width of 5. Mean here is just a single value. So what NumPy has to do to multiply that is to, we know it's going to be element wise, because each of those elements in the one array must be multiplied by the mean. What NumPy can do is just turn the mean into an array of the same size and multiply it element wise by the ones, which will also give us this result. So we end up with an array of 42s. So that's a handy thing that we're going to use quite often. So that's just a little example, but we're going to use an array that's the same size as our data, and so we can just pick out something we want it to be the same size as. So for example, if we want it to be the same size as the months, then I should mention actually that representation of the months that was used in the sea level data works really well for us. Remember, we encoded months as the year, and then a decimal, which is the proportion of the year represented by 1 month or 2 months or 3 months or so forth. That was really convenient for us because it gave us the values that we actually need along the x-axis to put things in exactly the right place. So we got this sort of for free, 1900, 1920, 1940 and all the things in the right place, and otherwise we'd have to do a bit more work to get that. So that's worked out well for us. Let's say we want to make a line of means the same size as the month. We just use ones like months, and then we can multiply that by the mean. The mean, remember again, is a scalar or just an integer, not an array, but NumPy can multiply them together. And we can check the length of months is 1339 and the length of the mean line is the same. So let's use this approach now to plot the mean or the average of our sea level readings on the same plot as the sea level readings. So what we can do, we can say, so the first, so we'll start at month 0. So our months is predefined for us because that's what we got from the data site. Okay, we want to get the first one and the last one so we know the bounds of our plot. So again, this is quite a common thing to do. So months 0 gives us the first one, months minus 1 gives us the last one. We're going to use linspace to get our x values between those two extremes, and we're going to get our mean line by multiplying that by ones like those x's. We could have done this a different way. We could have plotted them using the actual months. This way we get evenly spaced x's, whereas the months, remember, some of the months were missing, so they wouldn't be evenly spaced if we used the months to decide where we were going to get the x values for our mean line. In this particular case, it won't matter too much because we're going to be using plot, which is going to draw a line between the dots, so it's going to fill them in any case. Okay, so let's plot that. And there we are. So we've got a scatter plot with all our sea level values, and we've plotted our mean line in here, and we've used I think we've seen some of these before, but if you look at the API for plot, there's a whole lot of things that parameters you can set. So you can set things like the color and the line width to make it a bit more visible than the default. So remember, we've plotted two separate sets of x values here. Okay, even though they're on the same axis, the blue points, this is kind of important, and if you're debugging later down the track, you might find you plot something and you get a bunch of dots over here and you get a line over here and they're not in the same place or something. It's because plot allows you to use different values along the x-axis, and so the blue values that we've plotted are actually plotted against the dates, and the red values are actually plotted against our divided up x-axis in equal divisions. So two different things, but because the numbers coincide, if we'd done this from, say, from 0 to 1339, then, well, let's have a look at that. So we thought to ourselves, well, there's 1339 values, so let's do linspace that way. Okay, and we get something that looks crazy like that, and we think, what the heck's going on? Okay, so our linspace values have to be in the same range as our values for the months. Okay, here's our plot back how we wanted it. So we can see that this line is quite useful for identifying the trend that's going on here. And although we can sort of see by eye that it's increasing, comparing it with this line makes it much starker, because if you compare the number of samples below the line here with the number of samples above the line, clearly this is quantitatively a lot more below than it is above. And if you look up here, then the number above is quantitatively a lot more than below. So you can see how we're starting to work towards quantitative descriptions of our data, which sort of verify what we think we can see there. So we're going to take another little step towards that, and we're going to look at using our masking again to plot the mean for each century. So here we've got the mean for the entire swathe of data. What if we want to plot it for each century? How would we do that? Well, we can do it actually really efficiently, and this is where some of the things that we've been working on that have been quite, making slow progress, start to come together to allow us to do things, to do some really good things quite concisely and easily.